All right, so one of the other kind of tricky parts of this chapter is thinking a little bit about mechanisms and drawing those kind of arrow pushing. Um, so here we have, let's see, 1, 2, 3, 4, 5 different reactions. And what we're going to do is we're going to predict the products and then draw a mechanism, which is going to be those curved arrow formation from our base to our acid. We can also use the terms for Lewis from our nucleophile to our electrophile. So for each of these, we're going to need to identify what's our acid and what's our base. And then once we identify our acid and our base, thinking of what's our most acidic proton, and then going through and drawing the actual mechanism. So let's look at this first one. We have two different structures. We have the one on the left, which has two ketones in terms of functional groups, and then the one on the right, which has an alcohol and a ketone. That's not a carboxylic acid because there is two carbons between your oxygens, not one. So if we're looking here, one of the first things that I note is my first structure has a negative charge. That's going to be a carbanion. That's going to be kind of in between our two ketones. And anytime I see a negative charge, that's going to be a immediate hint that that is probably going to be a base. If this is going to be a base, then that means my other one is going to be my acid. And for that, I need to identify what's going to be my most acidic proton. And here I see that I have one explicitly drawn in connected to the oxygen. It's not always the case, but often if you have a hydrogen drawn in on your molecule, it's probably going to be the most acidic because you'll often draw in the ones that are connected to non-carbon things like oxygens and nitrogens, which are going to be more electronegative than a carbon. So at this point, I now have a base and I have my acid, I have my most acidic. So let's draw the mechanism. Now, I cannot draw my mechanism on my original structure here because this is not actually a correct depiction because I don't actually have all my bonds kind of drawn in. So I'm going to do this just a little bit under it. So here I'm going to explicitly show the lone pair of that carbanion. And then this alcohol, I need to show this bond. If I don't show this bond, I cannot show the mechanism because the second part of our mechanism is going to be breaking that bond. And if I don't see that bond, I can't draw the mechanism. So from a mechanism, I'm going to show my arrow from my base to my acid. So I'm going to start at my lone pair, and it's going to come and abstract that proton. That's now going to make this structure neutral, and I now need to have my consequence, which is going to be my breaking my bond and giving my lone pair. If I try to do this on my original structure, I don't have that bond shown, and if I do something like this, you will not get points for that because I don't see those electrons where I'm trying to draw arrows. So you need to redraw your starting material with the appropriate bonds and everything that are going to be breaking. Realistically, I shouldn't use that forward arrow. I should use some equilibrium arrows. And then my product here would be just the protonated version of my starting material, which is actually going to look the exact same. There's now two hydrogens. There was one originally and now a second one. But I'm actually not going to show them physically because we don't show hydrogens connected to carbons in our skeletal structures. And then my deprotonated version or my conjugate base, which is going to be the alcohol deprotonated. So this would be my full reaction, and then the mechanism is going to be those blue curved arrows showing the abstraction of that first proton and then making of my conjugate base. So this would be my kind of full drawn out mechanism and predicting my products. And we're going to do this now for 3 other ones to kind of get some practice on these. So let's go and look at our second one. Our second one here has an aldehyde. That aldehyde is that carbon double bond oxygen with a hydrogen on one of its sides and then a carbon on the other. And it's going to be reacting with diol H. Diol H is actually known as a really, really good reducing agent. And it is a well-known Lewis acid. We will actually talk about this in Orgo 2. when we do some discussions of oxidation and reduction reactions. This is really good at reducing aldehydes down to alcohols. And I'll show a specific example of that in the next, right after we kind of walk through this. So if this is going to be a really, really good Lewis acid, my Dibol, that means my other one is going to be a really good Lewis base. So in the case of my Lewis base, I'm going to need to identify where are my sources of electrons, because my Lewis base, which is also known as my nucleophile, so if I wanted to also write that down, nucleophile, and that makes my Lewis acid my electrophile. My nucleophile needs to be my source of my electrons. So where do I have lone pairs in my Lewis base? I have 2 sets of lone pairs on the oxygen, and that's actually going to be where we start. And this is a weird looking one, but it's going to follow the same principles as we saw like in our previous ones. We're going to have some curved arrows that are going to be from our lone pairs. Here, it's going to be on my oxygen rather than on a carbon with a negative charge, and it's going to attack my Lewis acid. Now, interestingly, this is actually going to form a Lewis acid-base complex, and it's actually not going to actually abstract the H on our Dibol just yet. It will eventually. And this will actually come and attack our aluminum. That aluminum is going to be the same as like our boron, and we did a few examples where we had aluminum, boron, and carbocation. Each of those are going to be examples of things that can form a complex. So here, rather than getting a separate acid-base complex, or sorry, rather than getting separate conjugate acid, conjugate base, we're going to have a complex. So we have a 6-membered ring, 1, 2, 3, 4, with our oxygen, and now I have a new bond to my aluminum, which has a hydride and then these little branch. My oxygen now carries a positive charge, and my aluminum now carries a negative charge. And this is my Lewis acid-base complex. And this is actually the key reactive intermediate in the reduction reaction that Dibol does. We don't need to actually know that for this course. You'll learn it in Orgo 2. But what will happen is this is actually will go on and do further stuff. And what will happen is this entire section right here will be reduced or decrease the amount of bonds to oxygen. And then this will eventually go down just to an alcohol. So you'll have an OH and then your H still on the other side there. So this is a reactive intermediate that will eventually break down and give you just an alcohol. This is a reduction reaction because we're reducing the amount of bonds to our oxygen and increasing the amount of hydrogens to it. So going from an aldehyde down to an alcohol is known as a reduction, and Dibol is a really, really good reducing agent. So it's not the greatest. Lithium aluminum hydride and sodium hydride are better, but it's a good reducing agent nonetheless. So you can take a aldehyde down to an alcohol using this, and this starts by a Lewis acid base step where the lone pair on this oxygen are going to come and attack the sp2 hybridized aluminum of Dibol. That's a weird one, but it's kind of cool to see how like a big complicated reaction that you won't learn until Orgo 2 actually is first step of the mechanism is something that is part of the very first types of mechanisms you learn in Orgo 1. And this will form that kind of big complicated complex that we've kind of seen previously. So in our next one, which is a lot more straightforward, we have this structure here. Go ahead and pause the video, take a few minutes, it might take you 5 or 10 minutes, to go through and try to identify what's going to be your acid, what's going to be your base, and then draw an arrow pushing mechanism for this reaction, and then kind of like predict your products. So go ahead and pause the video and take a stab at this one by yourself. Welcome back. Hopefully you actually paused and didn't make me just look stupid by just sitting here for a minute. And let's go and walk through this one. So the very first thing is I see I have a spectator ion. I see I have sodium, and my sodium, my potassiums, my calciums, my group 1 and 2s are going to be my spectators. And whenever I see those, I'm actually just going to eliminate those and then give me my minus. And we see that NaH, also known as sodium hydride, is actually going to be just a hydride, and that's going to be that hydrogen with 2 electrons and a negative charge. And seeing that I have this negative charge, this is going to tell me that this is probably going to be my base, making my alcohol species my acid. So anytime you see like sodium or lithium or potassium, erase it, make that a lone pair with a negative charge, and that is going to be your base. Now, I have to redraw my alcohol species, and I have to draw it so I have a bond that I can actually show breaking from my hydride. And here, this is going to be our traditional lone pair abstracts a proton, and then the electrons are going to go to form our conjugate base. That product is going to be this oxygen that's now deprotonated and carries a negative, and then H2, because I now have hydrogen bonded to hydrogen, which is a gas, is going to be our hydrogen gas as our product. So we're going to get our deprotonated version and then H2. Now that sodium is a spectator ion, so it's actually going to hang out, and I'll go ahead and show this in like a different color, right over here as my Na+, and then form a ionic bond with my conjugate base. If you wanted to be maybe a little bit more on the weird side, you could write ONA and H2. I will probably never write ONA. I will just leave that as O-, but that's where that spectator ion is hanging out. So hopefully this one was one that you're able to walk through, identifying that sodium hydride is just a hydride. That's going to be our base, and then it's going to follow our traditional Lowry-Bronsted, making a bond and breaking a bond, giving me my conjugate base and my acid. So let's go and look at our next one. Our next one's going to be a kind of unique reaction here, and I'll already tell you that this is going to be a Lewis acid-Lewis base. We have a ruthenium compound that's going to react with a compound that is called NMO. That's a short name for it. This is going to react with our ruthenium in a Lewis acid-base complex format. Given that information, that this is going to form a complex, go ahead and pause the video and then try to propose a mechanism for what would happen between these two. All right. Welcome on back. So in here, I see that I have a negative charge on my NMO. That's going to tell me that this is probably going to be my Lewis base. And then that makes my ruthenium my Lewis acid. In terms of a complex, that means that this oxygen is going to come and bind to my ruthenium. This is very not organic. This is very inorganic kind of chemistry, looking at a bunch of like ruthenium stuff. Most of like the weird Lewis stuff that doesn't do like your traditional Lowry-Bronsted are going to be more inorganic, and you'll actually see that in inorganic chemistry. And that's going to give us our ruthenium that is bonded to our oxygen, and then that goes down to our nitrogen, our oxygen, and this has an extra one. I'll draw in a bunch of lone pairs here. And then in terms of charges, this nitrogen still carries my plus charge. My oxygen was negative, and I got an extra bond, so it's now neutral. My ruthenium was neutral, but now got an extra bond. So it is actually going to be now negative, because I need that conservation of charges. 1 negative and 1 positive, 1 negative and 1 positive. And this right here would be my complex that forms by the reaction between NMO and my ruthenium. here my NMO is going to be my nucleophile, and it's going to be my source of electrons, and it's going to attack my electrophile, that electrophile being my ruthenium. That's going to form that kind of complex, and then this can go on to do other stuff, which is beyond the scope of our kind of original thing. The key thing we just want to do is think about what's going to be our base, and I'm going to choose this NMO because I see a negative charge. If I see a negative charge, I'm immediately going to be thinking about base, and then that can then go do some attacking of my electrophile, giving me here a specific complex. We can use those same kind of terms to think of the other one, though. So here, our hydride we can think of as a nucleophile attacking our electrophile. But when we abstract a proton, you get that 2 arrows. If there are no protons, then you'll just get that 1. All right. And for our last practice problem, we have kind of an interesting looking one. Here we have a deprotonated carboxylic acid and a quaternary amine reacting with a hydroxide. So go ahead and pause the video and think about which of these is going to be an acid and which of these are going to be a base. That's our first thing. So just start thinking about that first. Now, looking at these two, both of them have a negative charge. And you might say, Dr. Reck, you told me to look at a negative charge. They both have negatives. For our general kind of rule of thumb, when we think about your acid strength and base strength, they're kind of like inverted, where like if you're a really, really good acid, your conjugate is not going to be that good of a base, and kind of like vice versa. So in here, my hydroxide is going to end up actually being my base. That is going to be much better than my carboxylic acid. To kind of think about this, maybe like even if not even like think about relative strength, this lone pair here on this oxygen of just my base, which I've called my hydroxide, is going to be a lot stronger than that of my deprotonated carboxylic acid, because that carboxylic acid is going to be kind of like what I say, like arguing with itself. So it has resonance. So that charge is not going to stay just on that oxygen. It can also resonate and go up to the other oxygen. So rather than it wanting to go and do attacking, it's busy just stabilizing itself. So because of the fact that it's busy stabilizing itself, it's not going to be nearly as reactive for us. So that's going to mean that our thing on the left is going to be our acid, and the thing on the right is going to be our base. Now that we've identified this, go ahead and draw in your go ahead and make a mechanism. Draw a mechanism for a reaction where the base, which is going to be our hydroxide, will abstract a proton from our acid. Go ahead and pause the video and run through that. So I'm going to need to redraw it. And I'm going to need to explicitly write in the hydrogens, because they're going to be involved in bonding, and if I make a bond, I also have to break a bond in our Lowry-Bronsted. So I need to actually show which bond is actually being broken. So from a mechanistic standpoint, my hydroxide is going to come, it's going to abstract a proton, and then the bond between that nitrogen and that proton that's going to be abstracted is going to become a lone pair on that nitrogen. So we can draw this, our arrow would be kind of an equilibrium arrow, because this is an acid base, so it goes forward and reverse. And this would give me an NH2, which would be nice and happy, and then also give me water. The water would be my conjugate acid, and then the other one would be my conjugate base. And this would be kind of our product and our mechanism to get there. So start from our base to abstract a proton, and then the bond that is currently like still holding that proton needs to break to give us a lone pair. Now, interestingly, this can actually go on to do another reaction. So if I then think about our two structures here, rather than just doing the reverse reaction where this NH would go and grab a proton from our water to go back to our original, here we can actually see a slightly different type of transformation. Let's see how much space. Oh yeah, I got tons of space. Where I can actually see this act as my base and this act as my acid, where I can see my base come abstract a proton, kicking out my lone pair to that OH, giving me like a protonated version of my carboxylic acid, NH2, and my OH minus. And this is also in equilibrium. And all of these can kind of exist together. So hopefully that kind of gives you a little bit of practice. With drawing mechanisms, it really does come down to practice, practice, practice. In general, you want to identify what is going to be your nucleophile or your base. That's going to be the thing that has your electrons. If you have a negative charge, focus in on that immediately. If you might have a negative charge that's hidden by a spectator. So if you have a sodium or a potassium, you might focus in on that to kind of erase that. We saw that back at the beginning up here with our sodium hydride. If I see like a sodium or a potassium or calcium, that's kind of like a hidden version of a charge. And then if I don't have any choices, I don't have any actual like charges, either permanent or hidden, then I'll often think like, okay, do I have a lone pair on something that is electronegative? Do I have a lone pair on a nitrogen or a lone pair on an oxygen? That's kind of like my thought process of trying to like identify the base. And then that's going to, most of the time, abstract a proton, as we've kind of like shown down here, where you have a bond, you're going to have an arrow, which is going to show the formation of a bond from your base to your H. That H is going to be abstracted as a proton, not as a hydrogen. So those electrons are going to stay, and we're going to show those electrons staying by doing a little baby arrow from that bond to your atom. And that's going to be the kind of formation of our conjugate base. That's going to be what we'll do the vast majority of the time. However, if you do have something that doesn't have the ability to do a proton, then you can do the Lewis acid base stuff where you form that complex. And that's our kind of practice on a bunch of mechanisms. We'll do a little bit more practice in class when I am back. But we're going to stop there, and that's kind of a good feel for kind of our Friday review session.